We learned in our last video about sine and cosine, those definitions, which I called the foundation of trigonometry, and it's really true. We're going to find some ways to discover the values of those trig functions for the three most famous angles. The three most famous are 30, 60, and 45. These are the foundational angles that we'll be using repeatedly throughout the whole course. We're going to use these to build different sine and cosine values all the way around the circle. But before we do, we first need to learn how to just find the basics here in this first quadrant. So they've put the right triangle inside the circle, which again, we're going to get back to that. But we want to just figure out how do we find the values of 30, 60, and 45 for sine, cosine, and tangent, and all the others. Well, the first thing is to talk about converting between the two. So 30 degrees is also pi over 6 in radians. 60 degrees is pi over 3 in radians, and 45 is pi over 4. So we can just go back and forth between these special angles, just converting between whichever system you want to be working with. Okay, now this one is pretty intuitive why this would be the case if you use the Pythagorean theorem. It turns out that across from any 45-degree angle, you could call it just whatever the length of the side is. It's just s. We're just going to call it s. So both of these would have to be the same size, of course, because they have the same angle. If you use the Pythagorean theorem, it turns out the hypotenuse is always going to be the square root of 2 times s, no matter what the side is. And we can use this idea to build the values of sine, cosine, and tangent for a 45-degree angle. Now, perhaps not quite as intuitively, we could use, it's still based on the Pythagorean theorem, but we could say next to a 30, well, let's do a cross. So this pi over 3 is a 60-degree angle, same thing. The side across from it, opposite, it's always in the ratio the square root of 3 times whatever the side is. The side next to it is always just the side, whatever that length is, and the hypotenuse always makes 2s. Now, there's going to be we're going to memorize these, and we're not going to need this triangle approach to do this after probably the next video. I can't remember, but very soon. But for now, we could use these ratios that no matter what the side is, we could find the values of 30, 60, and 45 degrees. Now, let's take a look and see what this would be like. So, I was hoping for a triangle here, so let me make one. All right, so we're going to make a right triangle, and this angle is pi over 3, which is the same as 60 degrees. So if we go back, here's what we said. Across from pi over 3 is radical 3s. Every time. And next to it is s, adjacent, and opposite is 2s. I don't have these memorized, so I got to think that through a little bit. Okay, so these are always the way, the ratios. Now, no matter what the side is, they stay in this same proportion every time, because we saw they're similar triangles with that angle. So we're just going to use these ratios, and we're going to find all of our trig identities. So sine of pi over 3, pi of 60, is opposite over hypotenuse. So that would create radical 3 times s over 2s. But look what's going to happen. The s's could just be canceled out. And so the sine of a 60-degree angle, pi over 3, is always going to be radical 3 over 2. Now, how about the cosine of pi over 3? Well, that's always going to be the adjacent over hypotenuse, so that's s over 2s. If we cancel down the s's, we get 1/2. How about the tangent of pi over 3? Well, that's opposite over adjacent, so opposite, radical 3 over s over s. S's would cancel, we'd get radical 3. Now, we can just flip all of these upside down. If we want, does it want all 6? Yeah, it does. So why do they do that? I don't like that. So this is the cosine flipped upside down. Remember, they're the ones that are partners. Cosine and secant. We flip that upside down. 1/2 upside down, we would get 2. These are partners. Sine and cosecant are partners. So we flip those upside down. Now, look what they did here. They flip it upside down, you'd have 2 over radical 3, but they rationalized the denominator. And we get this here. Okay, tangent is radical 3, so if we flip it upside down, we have 1 over radical 3, but if we rationalize the denominator, we get radical 3 over 3. All right, so let's play the same game. They want us to do this for pi over 4. Okay, so this is always going to be s and radical 2s every time. So we can just start making our trig functions. The sine of pi over 4, which is opposite over hypotenuse, so it'd be s over the square root of 2s. Now, the s's would cancel, and I'd have 1 over the square root of n, or the square root of 2. We're going to rationalize that. Remember, that means multiply the top and the bottom by that radical. And I'd have radical 2 over 2. Now, cosine is pi over 4 of pi over 4. Do you see it's going to be the same thing? So cosine is going to be adjacent over hypotenuse, but all the values are the same. So we're going to still wind up with radical 2 over 2. Tangent of pi over 4 is going to be the opposite over the adjacent. Well, that's s over s. And that's 1. Okay, so let's go through our inverse. Let's go through their partners, their reciprocals. So sine's partner is cosecant. If I turn that upside down, now I'm going to jump back here. You could do this a couple different ways. Well, I'll just make this less confusing, and I'm going to make this 2 over the square root of 2. So you rationalize that denominator, and you're going to get 2 square root of 2 over 2. Cancel that down, you get radical 2. This is what I was saying. You could have flipped this over back here, and you wouldn't have had to rationalize. 1 over radical 2 is the same thing, so I could have flipped him. Okay, secant of pi over 4 is going to turn cosecant upside down. So anyway, it's the same numbers. We're going to get the same thing. So we're going to get radical 2. Cotangent of pi over 4 is going to turn 1 upside down, which is going to do nothing. It's going to get you the same thing. Okay, now let's talk about it's called the cofunction identities. Identities are going to be a really important principle here that we're going to need quite a bit as we get more advanced. But identities are laws. They're rules that always hold true. And so here's what we're saying. Okay, let me go back to my ratios here. I don't have them all again, sorry. Okay, so across from 30 is s. Across from 60 is radical 3s. No, I'm on the wrong one, 2s. Okay, so here's what this is saying. If I did the sine of 30, I'm going to get opposite over hypotenuse. I'm going to get s over 2s, which is 1/2. Well, it kind of makes some intuitive sense that the cosine, what this means is, okay, well, this is in radians, but let's take it away. It'd be the same as 90 minus t. In other words, if I take 90 minus 30, I would have a 60-degree angle. And why is that? Well, because if this is 90, these are always going to have some kind of special partnership, because if one's 30, like, they add up to be 90 degrees. So because this is 90, these are always going to be the partner values. This is going to be one angle. 90 minus that value is always going to be the other one. They're always going to be in the same triangle. Now, if sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, look what happens. So the adjacent to 60 is still s. So 30, these identities are saying the two partner angles are pointing to the exact same sides. Do you see what I mean? So sine called him opposite and cosine said adjacent, but these because they're partner angles, it means he's in this position here, 60's in this position here. They're referring to the same side. Does that make sense? So because one side is 90, these two add up to 90 every time. The other two always add up to 90. And so sine and cosine are always going to be referring to the same thing. So sine's calling it opposite and cosine's calling it adjacent, but they're both pointing to that same side. Okay, so here's kind of a weird way to say it here, that I don't really know the name of t or what the angle is, but I know that I want something to do with the cosine of his partner. T and pi over 2 minus t have to be partners in the same triangle. And so if sine is 5 over 12 and this is his partner, they're referring to the cosine of this angle, they're referring to the exact same value. They're pointing to the same side. So sine of t is going to get you the same thing as cosine of his partner angle because they're referencing the same side. So if sine of t is 5/12, cosine of 90 minus t, or pi over 2 minus t, is pointing to the same two sides. Okay, now cosecant and secant are in that same relationship. They're based on sine and cosine, so they have that same property. This is 30 degrees, pi over 6. This is 60 degrees. Well, these are the same. These are the partners inside of a triangle. These are the two that add up to be 90. So if the cosecant is pi over 6 and these are the partner angles, well, then it's going to have to be referring to the same sides. So the secant of pi over 3 must be getting you the exact same thing. Now you got to use the partner angle, and you got to switch from 1 to the partner trigonometric function. But if you do that, switch from one angle to his partner angle, and if you switch from one trigonometric sign to his partner trigonometric sign, you're going to get the same value. Okay, so we're going to see some better ways to kind of do this, but it's a good introduction, and it is true. You could, throughout the whole course, you could use this idea to get those basic sine and cosines of 30, 60, and 90, or 30, 60, and 45. But we're going to just see how we're going to memorize it very soon. It's going to be really easy to do.